All right, hi everybody. Thanks for tuning into the video today. We're going to be continuing to look at functions, particular function notation when it comes to increasing and decreasing functions. I think we have an idea what it means for a function to be increasing or decreasing, but what does that look like? How do we write that out using function notation? And then I'm going to be looking at a particular type of function called a piecewise function. They're really interesting. I don't know how much you've seen them before, but we'll take a look and get an understanding of piecewise functions as well. So, what does it mean for a function to be increasing or decreasing? Okay. Well, I've got increasing, decreasing constant over here, and I have a and b. And in each of these cases, I'm saying if a is less than b. Now, those are x values, so we need to get visual here. So let's say that this is a and this is b. A is less than b. Do you agree with that? A is to the left of b on the x-axis, so a is less than b. Now, if the function is increasing, now we know increasing to mean going up. So from left to right, it's going up. Let me just draw something that would look like that. So this function is an increasing function, okay, from left to right. Now, how do I write that? A is less than b implies what? Well, if I take a look here, at a, that is the y value of the function. And what do we call the y value of the function at a? That's f of a, right? We put a into the function, we get out f of a, the y value, so that's f of a. Here we go, right up here. What's the y value there? I could extend this out maybe a little bit longer or slide this up. That's f of b. Okay. So here's an x value of a, the y value is f of a. X value of b, y value f of b. So if the function is increasing, says that if a is less than b, how would we compare f of a and f of b? F of a is less than f of b. So if we look along our vertical axis, our y values, f of a is less than, it's lower on the y-axis than f of b. So it's increasing if a is less than b, if f of a is less than f of b. How about decreasing? We still have a is less than b on the x-axis. Now we're going to draw a decreasing function. Maybe our decreasing function is a line. Looks like that. Well, what's the y value right there? That has a y value of f of a. Right here, at x equals b, that has a y value of f of b. So if the function is decreasing when a is less than b, how do we compare f of a and f of b now? F of a is greater than f of b. Good. Last one, constant. What's it mean for a function to be constant? Okay. It means it doesn't change. Okay. That means no matter the x value, the y value is always the same. A constant function would be a horizontal line. It's not changing, is it? Okay. How does f of a compare to f of b now? There's f of a. And right here is f of b, and what's true? They're equal, aren't they? If we have a constant function, f of a equals f of b. Okay, so again, I think the concept of increasing, decreasing, and constant is something that you guys already understand, but this is how we write it. This is how we use function notation. This is why saying things like f of a and f of b is helpful instead of just saying y. All right, so here's a function. Okay, I want to identify the intervals on which this function is increasing, decreasing, and constant. Okay, I gave us a little bit of help by coloring the different parts of the function different colors. So where is this function increasing? Well, from this point on, from there to the right. Now what is the x-coordinate of that? That's 0, that's 5, that's at 2. This function is increasing from 2 to infinity. Now I'm using interval notation. Okay, I'm going to put a parenthesis on 2. Okay. At x equals 2, is that function increasing? Well, how does just a single point be increasing or decreasing? We have to look at open intervals. So we do not include 2, because 2 would actually be part of this one section of the function as well, that piece, and that piece is constant. This over here is decreasing. Okay, so it's decreasing from x equals negative infinity to 0, but we're not including 0. And then it's constant from 0 to 2. And again, we don't want to include the 0 and the 2. They're a part of those others, and those are just points. And a point itself can't be increasing, decreasing, or constant. Now, if you look at this function, have you ever seen a function that looks like that before? It's a bit different, isn't it? It's almost like there's different pieces to this function. To the left of 0, it looks like this. Okay, almost like a parabola. To the between 0 and 2, it looks like a horizontal line. Okay, from the right of 2, it looks like a line with a slope of 1. Okay, this function that I graphed here has different pieces. And when we do that with functions, we call that a piecewise function. It uses different formulas, different equations for different parts of the domain. Okay, so here's an example of a piecewise function. Okay, our function f of x equals, well, it's equal to x plus 1 for x's that are less than negative 2. X is less than negative 2. That's what it is. Now, from negative 2 to 3, including negative 2 and 3, this function is equal to 5. And then greater than 3, it's equal to x squared. So we have the different formulas, these different outputs, depending on where in the domain we're looking. So let's evaluate our piecewise function at different x values. F of negative 5. All right, that tells me x equals negative 5. Which part of the domain is that in? Negative 5 is in this domain. Negative 5 is less than negative 2. So we use this part of our piecewise function and say this is going to equal negative 5 plus 1, which is negative 4. All right, how about f of 0? Where in the domain, in which one of these pieces does x equal 0? And there, 0 is between negative 2 and 3. So f of 0 equals, between negative 2 and 3, it's 5. No matter the x value, it's that constant function. F of 0 equals 5. F of 4. Okay, where does 4 fall? Falls into the bottom one. So we know f of 4 is going to be evaluated by taking 4 squared and getting 16. You know, let's add another one in here. F of, let's add 2 more. Let's go f of negative 2, and then let's find f of 3. How do we get f of negative 2? Where does that fall? Well, there's a negative 2 here, there's a negative 2 there. Okay. Where is it equal to negative 2? That's in this one. 5. How about f of 3? It's in that same piece of our function, isn't it? 5. All right, let's get to the number 4 here, kind of an interesting one. Find f of b plus 1 if b is greater than 2. So we have to figure out which part of our domain are we looking at. Now they said b is greater than 2. Notice that's not an x, is it? Okay. This is the x. Okay. Well, if b is greater than 2, then b plus 1 must be greater than 3. And remember, b plus 1, that's the input. This is the x. So that tells us x is greater than 3. So which part of our piecewise function are we in? We're in that one. Now, what are we putting into the function? F of b plus 1 equals, we need to put b plus 1 in for x in there. This is b plus 1 squared. All right, so that's how we evaluate our piecewise functions for different x values. I think the graphs get even more interesting. So let's look at some graphs here. Let's graph a piecewise function where f of x is 1/3 x plus 3 for x's that are less than 3, and f of x equals negative x for x's that are greater than or equal to 3. Let me get x and y axis up here. So how do I go about graphing this? Well, I have to think first off, what does this first one look like? 1/3 x plus 3, we know that's a line. The y-intercept is 3. The slope is 1/3, up 1 over 3. So I graph this just like I would graph any other line. There we go. Okay. So that's what 1/3 x plus 3 looks like. We know that. We know what graphs of lines look like. Now, this tells us, though, this is only for x's that are less than 3. So let's look at our x-axis. And we're only going to have it be this line for x's that are less than 3. 3 is right there, so that means we have to get rid of all of this part of the line. We've got to bring it all the way back to 3. Now, even one step further, it didn't say for x's less than or equal to 3, 3 should not be on this line. So what do we have to change this point to? We have to change it to an open dot, because this line goes up all the way to x equals 3, but not including it. So that's an open dot. Now, we're going to graph y equals negative x for x's that are greater than or equal to 3. Negative x, slope of negative 1, y-intercept of 0. There's my y-intercept. There's my, I don't know if I said that right or not. Slope of negative 1, y-intercept of 0. The y-intercept 0, there's my slope of negative 1, down 1 over 1. If I were to graph this, it looks like that. However, we only need to graph this for x's that are greater than or equal to 3. So I need it to start right there and include that point because it's greater than or equal to 3. I have to get rid of the function for all of that. So the way I'm going to do it here in my program, I'm going to put another point there so I don't forget what it is. I would just erase this, but I don't want to accidentally erase my blue line. So I'm going to start at 3 and go that way. There we go. That's our piecewise functions graph. Isn't that cool? Okay. We get to follow this line up to 3, but right when we hit 3, we jump down to that point and we follow that line. Let's look at another one. All right, graphing 3 parts, 3 pieces to this piecewise function. 4 when x is less than or equal to 0. 4 minus x squared from 0 to 2, including 2. And 2x minus 6 for x's that are greater than 2. All right, f of x equals 4. Constant function, horizontal line. So here we come, 1, 2, 3, 4. And it's going to do that all the way up to 0, but we have to stop at 0. Open dot, nope, check that, less than or equal to 0, close dot. Okay. Now, from 0 to 2, it turns into 4 minus x squared. Now, we should recognize that as a quadratic, so we know the graph's a parabola. If I were to rewrite 4 minus x squared, that's negative x squared plus 4. And thinking on our prior knowledge, hopefully we recall how to graph that. We know parabolas are U-shaped. The negative is going to do what to our parabola? Flip it. The plus 4 is going to move it. Good, up 4. So my parabola normally would have looked like this with those points. I'm going to reflect them. And then I'm going to slide them up 4. Look at that. It's at the same point there. That already was a closed dot. It's going to remain a closed dot. Move this one up 4. That one up 4. This one up 4. That one up 4. I've got to get rid of all the extra points here. Okay. Now this parabola then would look like that. But let's recall the domain for this piece of the function. 0 is less than x, which is less than or equal to 2. So are we going to have anything to the left of 0? Okay. And we're only going to go up to 2. So if I were to do this again, okay, I need to get rid of the left part. I need to start with an open dot at that point. Now, if it's open dot over a closed dot is a closed dot, and then it's going to come down here, and it's going to include the point 2, 0, and that's where it's going to stop. So this is my quadratic there. Then we've got 2x minus 6 for x's that are greater than 2. Y-intercept is negative 6. Slope is 2 up 2 over 1. And there's my graph. Now remember though, we're starting at for x is greater than or equal to 2. So I'm going to find x equals 2 is actually this point right here. That needs to become an open dot, and I need to get rid of everything else this way. Okay, and here's my piecewise function. It follows a constant function. It's part of a parabola. Okay, and that's a smooth transition. Every point is in there. That dot is closed. And then from there, it's going to jump down here and come up on that positive sloping line. All right, let's look at one more together. Okay. Stepping it up a bit here. F of x is x squared minus 4 over x plus 2 for x's that are not equal to negative 2. And then for x is equal to negative 2, it equals 3. Okay, so this is interesting. Everywhere except for x equals negative 2, it's this graph. Now, why might that be? Well, hopefully you're recognizing that if we put negative 2 in for x here, we get 0 in the denominator. In fact, we get 0 in the numerator as well. Okay, we can't put in negative 2 to this function. So what we're doing here is we're saying, okay, we can't put negative 2 into this one. So we're going to tell the function what it should equal when x is negative 2, because we can't use that. Now, what's the graph of this look like? Well, you might notice something when you look at that numerator and that denominator. Do you notice that the numerator is the difference of perfect squares? That's something that we can factor. That's x plus 2, x minus 2. And that's over x plus 2, isn't it? We worked on this in the past. Those x plus 2's cancel. This is equal to x minus 2. So this x squared minus 4 over x plus 2 really equals x minus 2. It's a line. Its line has a slope of negative 2, or excuse me, a y-intercept of negative 2 and a slope of 1. there it is. But do you remember that x can't equal negative 2? If we put negative 2 into this, we'd end up with 0 in the denominator. So we need to go to negative 2, and we need to put an open dot. I can't draw a good circle here. Yeah, it's kind of nice, a big circle there. Clearly, there's a hole in our graph. Okay. So now we just graph the top. Okay. Now, when x equals negative 2, what is our y value? Our y value is 3. So we have this additional point at x equals negative 2. We're actually going to set it equal to that. Okay. So our graph is a line with a hole in it when x equals negative 2, okay, where we instead take that y value of 3. Okay. Now, this is just the function that we're given. Maybe we want to say it should equal 0. What changes then? Boom. What might it make sense to change this to? Maybe not 3, maybe not 0. Maybe it would be helpful for us to say that it should equal negative 4. Because now if I say it's equal to this, for x is not equal to negative 2, because we can't put it in anyway. Okay. But when x equals negative 2, it equals negative 4. What does that do? That fills in the hole in the line. Okay. So maybe, depending on the situation, we might want to make a piecewise function that does this. To say, okay, we know we can't put it in there, but maybe we should define it so there's not a hole in our line. But if we go back to the original, it looks like that. Okay. Let me open up here real quick Desmos. Okay. And I just want to see what this looks like when I graph it in Desmos. F of x equals, on the top we had x squared minus 4. On the bottom we have x plus 2. Okay, and we see here we get that line that we talked about. Does this line have a hole? Yes, it does, doesn't it? Now you got to put the cursor over it here in Desmos to see that hole, but there it is. And then we say f of x, f of negative 2. Well, there's a few ways that we could write this. We could say f of x equals, my parentheses are over here, I'm bumping my microphone, I'm sorry. F of x equals 3, but we don't want all of those, we only want it for x equals negative 2. Why is it not showing it? Okay, maybe we don't want to write it that way. Maybe we would just want to say f of negative 2 equals 3. I don't know why it's not plotting that point. Desmos is not cooperating. I do want to show you this if you are graphing things in Desmos. So part of one of our functions that we graphed was 4 minus x squared, but we only want it for x's in a certain domain. So I'm going to put my curly bracket, and I'm going to say 0 is less than x, which is less than or equal to 2. Okay? That's how you graph a piecewise function in Desmos. Curly brackets. Okay. And then I could do that last one. I'm trying to remember off the top of my head what that function was. 2x minus 6. And that is for x's that are greater than or equal to, nope, I think it was just greater than 2. There it is. Cool stuff. Well, thanks for tuning in. I'm hoping you're able to piece things together as you've learned this. We'll see you later.